All right, in this video, we're going to take a look at integration via substitution. So I'm going to find some indefinite integrals using the technique of substitution. So integrate with the technique of substitution. Now, we've already integrated by using some of reversing the basic rules of derivatives. So when you integrate, you're finding antiderivatives, which is the reverse of derivatives. So we saw previously how the basic rules can be reversed, how some of the basic rules can be reversed. But hopefully you saw in Calc 1 some of the more complex derivative rules. So now we're going to reverse them. In particular is the idea of the chain rule. In Calc 1, when we took a derivative of the composition of two functions, f of g, where g is our inside function, we ended up with f prime composed with normal g and then multiplied times the derivative of the inside function. Now, you may have seen in different classes, different notation, but this is the basic chain rule. We have a composition of two functions, and we want to take a derivative of the composition. So the derivative becomes the derivative of the outside function, where our input is the normal inside function, and then I multiply times the derivative of the inside function. So let's do an example. If I have capital F of x equals this polynomial raised to the 7th power, then when I take a derivative, the derivative of the outside function. Now, the outside function is the operation of raising to the 7th power. Therefore, the 7 is going to come out front, and our power is going to reduce to a 6. The inside function there of 3x squared minus 2x plus 5 stays the same. But on the outside, I have to multiply times the derivative of the inside function. Now, this derivative, the derivative of 3x squared minus 2x plus 5, is 6x minus 2. So I'm going to get 7 times my original polynomial raised to the 6th power times the derivative of that polynomial. That's how the chain rule works. Now we want to reverse the chain rule. And so we're going to come up with a process of reversing the chain rule. The first thing we're going to do is I'm going to replace this g of x with the letter u. So if I replace the g of x with the letter u, then u is some function of x. And then my chain rule says taking a derivative of f of u is equal to f prime of u times u prime, where u prime is the derivative of u with respect to x. So I get this, which is a little bit nicer to look at than this, but all we're doing here is replacing the g of x with a letter u. And then what if I were to integrate both sides? Now, if I integrate the right-hand side, I just get f prime of u times u prime. And if I integrate the left-hand side, I just get f of u. Now, there'll be a plus c here at the very end, so I can ignore any plus c's going around because I can tack one on at the end. So this tells me a way for starting at this right-hand side and doing an integration. Basically, this is the concept of substitution. We are going to replace some inside function with a variable u. When I do that, I have to consider that u prime at the end. So the way that it works is I'm going to go from integrating with respect to x to integrating with respect to u. And this is going to force a change in the differentials. So I'm going to be integrating with respect to x. I'm going to be using dx. And then I'm going to change to integrating with respect to u. I'll be using a du. But when I do that, I have to take into account this g prime because remember, u was equal to g prime. So we're going to end up having to replace not just dx with du, but some g prime dx with a du. It'll make more sense once we start with some examples. So let's go ahead and do that with this example. Use substitution to integrate 100 times the quantity 4x minus 3 raised to the 6th power with respect to x. So this is an indefinite integral integrated with respect to x. Now, the biggest thing we have to do in every single substitution example is we have to decide what that inside function is, because that's going to set everything else. We have to figure out what the inside function is, what the u is, and then we'll adjust the differentials. All right, so in this case, the inside function is the interior polynomial that's being raised to the 6th power. So u is going to be set equal to 4x minus 3. Now here's what we do. We take a derivative of u with respect to x. Notationally, that's du over dx. Now, weirdly enough, this is an operator, not a fraction, but we'll talk about that later. So derivative of u, again, think of this as function u is equal to 4x minus 3. Derivative with respect to x is just going to be a 4. Now, here's the thing. Even though this is an operational, these are operators here, this is not technically a fraction, you can still kind of pretend that it is a fraction and multiply both sides by dx. Again, there's a little bit more to it than that. These are differentials, not numerical values. But essentially, what's happening is that now 4 times dx can be replaced with a du in this integration. And the 4x minus 3 can be replaced with a u in that integration. Now, here's the dx tacked on to the end. Let's see. So here's the dx tacked on to the end. And there's one of two options that I can do. Knowing this equation and seeing that we have a 100 out front, what I can do is I can break that 100 into 25 times 4. And because multiplication is commutative and associative and all of that, I can take that 4 and put it in the back part of my integration next to the dx. Now this 25 dx excuse me, now this 25 times 4x minus 3 to the 6th power times 4 dx. Now we can do the substitution on that. So we're going to get 25. This 4x minus 3 can get replaced with a u. So that is just going to be 25 u to the 6th power. And then the 4 times dx can be replaced with a du. So we went from integrating with respect to x now to integrating with respect to u. We've essentially repackaged our integration in a way that's easier to integrate using our basic rules. Now here's the thing, u to the 6th, if I'm integrating with respect to u, then u is just the variable I'm using, and I can use basic rules for integration of u to the 6th. We know how to do that. We're going to go u to the 7th and then divide by 7. So we get 25 over 7 u to the 7th plus c as the integration there. Now, this is my answer if I wanted to keep u as my variable. But since my original integration started with having x as the variable, I'm going to change it back so that the antiderivative is with respect to x. So instead of having u to the 7th, I'm going to say, well, actually u originally was 4x minus 3. And so my final answer is just that, 25 over 7 times the quantity 4x minus 3 raised to the 7th power plus my constant. And that's what we're going to do in a lot of these substitutions. Basically, we set up, we figure out what the inside function is. When I take a derivative of that inside function, it tells me the differential exchange that I need. And then sometimes I may rewrite my integration so that I get a nice differential exchange. We'll see other options later. And after I do my substitution for u, then integrating with respect to u should be fairly straightforward. And then I repackage that and write my final answer with respect to x. So this substitution went from integration with respect to x to integration with respect to u. I do my integration, finding the antiderivative, and then we substitute back so that it's done with respect to x, so that my final answer is written with respect to x. Let's do another example. Let's integrate 8x minus 20, quantity 8x minus 20, times quantity x squared minus 5x plus 18 raised to the 10th power. So this is an example where we can use substitution to integrate. As always, the most important thing is to figure out the inside function. In this case, we have two functions on the inside of parentheses, but only one of those has been raised to a power. Well, this one's raised to the implicit power of 1, but this is raised to the power of 10. So my inside function in this case, I'm going to use, for my inside function, I'm going to use x squared minus 5x plus 18. All right, so here we go. Like I said, inside function is going to be the one that's being raised to the 10th power. So x squared minus 5x plus 18 is what I'm going to call my u. Now, we take a derivative of that u with respect to x, and we would get 2x minus 5. This chapter, this section, this video, and a lot of the other integration technique videos heavily rely on you knowing how to take derivatives. So this means that the du is equal to 2x minus 5 quantity times dx. So that's my differential exchange. Now, I don't have necessarily a 2x minus 5 in my original integration, but you'll notice that 8x minus 20, if I factor out a 4 from that, I'll get a 2x minus 5. So in this case, what I can do is I can factor out a 4, and I'll be left with 2x minus 5 times 4. And during the next step, what I can do is I can basically, again, because of associativity and commutativity of multiplication, I can take that 2x minus 5 and put it in the very back along next to the dx. I like to do this just for the visual. You can obviously do it here as well and be just good to go. Now, for a moment, I'm going to highlight some things just so that we know what's going on. This 2x minus 5 dx, that is going to get replaced with the du. So let me highlight that. And then this x squared minus 5x plus 18, that's going to get replaced with the u. So again, I know I highlighted this, but essentially that integration is the same integration as 4 times u to the 10th du. Now that is an integration that's fairly straightforward to calculate. So once I just use my basic rules, because now I'm integrating with respect to variable u, and u to the 10th is just a polynomial with respect to variable u. So I get 4 over 11 times u to the 11th plus c. I'll always use a capital C. So that's how I integrate that. I get my answer of 4/11 times u to the 11th plus c. And then I can sort of replace the u, because my original integration was done with respect to x. I'll replace that u with my original substitution of x squared minus 5x plus 18. And so that's my final answer for finding the antiderivative, or finding the class of antiderivatives of my original function. So when I integrate 8x minus 20 times quantity x squared minus 5x plus 18 raised to the 10th power with respect to x, this is what I would get. And by the way, you can check that by taking a derivative as well. If I took the derivative, the 11 would come out front. We would get 4 times x squared minus 5x plus 18 raised to the 10th power. And then I'd have to multiply times the derivative of the inside function, which would be 2x minus 5. And then when I rewrite that, the 2x minus 5 times 4 would give me the 8x minus 20 I was looking for. So that is always one way you can check, is to just take this, find the derivative of it, and that'll check. Obviously, it doesn't ask me to do that, so this is all we need. Let's do another example. And at this point, if you want to, you can pause and try this example on your own and then restart the video and see if you got it right. But I'm going to do it right now. So if you want to try it on your own, pause at this point. So when doing substitution, the first step is always to determine what the inside function is. Here we have x times something squared dx. I'm going to let the u be equal to 3x squared plus 5, because that's the polynomial inside raised to a higher power. So when I take a derivative of u with respect to x, I get 6x plus 0, which means that I'll have this differential exchange of du is equal to 6x times dx. Now, if you wanted to, there is an implied 1 out front. So you could take that 1 and factor it into 6 times 1/6. But I will also be able to take this x backwards and pair it with the dx. So in other words, I can put the x there in the back. And in that case, what I can do is I can say, well, x times dx, this is 6x dx is equal to du. I could have also stated that 1/6 times du, the differential, du, is equal to x times dx. In other words, I could have divided both sides by 6. And now I can replace this x dx with a 1/6 du. So that's how I'm going to do it this time. If somebody else wants to instead factor 1 into 1/6 times 6 and then pull the 6 back, that's perfectly fine. We're going to get the same thing in the end. So this 3x squared plus 5, that's what my u is. So when I do my substitution, I'm going to get u squared. X times dx is 1/6 du. And usually we like writing our coefficients out front. So I'm going to write 1/6 times u squared times du. I'm going to write my integration that way. This is an integration using basic rules. So raise the exponent by 1, divide by the new exponent. We're going to get 1/18 u to the third plus c when I integrate. Again, the du goes away because we're integrating. This becomes the antiderivative of this function, which through substitution means that 1/18 times 3x squared plus 5 raised to the third power plus c is the antiderivative of 3x squared plus 5 squared times x dx. So that's the antiderivative that we're looking for, or the class of antiderivatives. because technically C can be any number. So this is the class of antiderivatives, and that is my final answer. So that's just an example of, again, utilizing a different approach. Here we had a 6 on the right-hand side. We moved it. We divided both sides by 6 to get rid of it. And that may have been an easier substitution to do. In my original problems, I could have done that as well. For instance, up here, I could have divided by 2x minus 5 and then replace the dx with a 1 over 2x minus 5 du. That's a little bit more cumbersome in this one. So what's the, when should I factor out the coefficient? When should I turn this 1 into a 1/6 times 6 versus when should I just leave it alone and do a division at this step? Well, that's kind of up to you. And sometimes it's easier to just leave the number in. Sometimes it's the same. Sometimes it's easier to divide. Sometimes it's easier to factor that coefficient. Sometimes it's easier to divide down here. You'll get the same answer either way, though. So just kind of preference and how much time certain operations take you. Also, the more you work at it, the more comfortable you'll be getting choosing one way or the other. Now let's do this example. We're going to use substitution to integrate this one. And this, obviously, we're not doing a polynomial raised to a power. Well, we're kind of not doing that. We kind of are, though, as well. I'll show you how to do this in just a moment. If you want to try this on your own, you can. By the way, I said this is not like a polynomial to a power. It kind of is, though, because we could have rewritten this as the integration of x times x squared plus 1 raised to the -1 power with respect to x. So we are going to let our u, the inside function, be that x squared plus 1. And therefore, the du with respect to x, the derivative of u with respect to x, would be 2x. I'm going to do this differential exchange. I'm going to say du is equal to 2x times dx. And then because I have a single x up here and I don't have 2x, what I'll do is I'll divide both sides by 2. So the differential exchange that I will use is 1/2 du is equal to x dx. And then we're good to go. So I'm going to rewrite this once again. I'm going to pull the x, kind of pair it up with the dx. If I do that using the properties of fractions, if I factor out an x, I'll have a 1 on the top. So I'll have 1 over x squared plus 1 times x dx. Again, I'm just factoring out that x using properties of multiplication. So now I can do my substitution. My substitution is going to give me 1 over u times 1/2 du. Now, I'm going to write the 1/2 out front. 1 over u du times 1/2. Well, that 1/2 can be brought outside of the integration if I'd like. That's not going to affect anything. That's just a constant multiple. But when we integrate 1 over u with respect to u, we get natural log. So I get 1/2 times the natural log of u plus c. That is the antiderivative. And now I know what the u is. U is x squared plus 1. So I'm getting 1/2 times the natural log of x squared plus 1 plus c. So that is my antiderivative. I like to write parentheses around this. Obviously, some people would write absolute values. In this case, you're always going to get a positive number anyways, but I always write parentheses around this argument inside of natural log. So that's how it works. So that is the antiderivative of x over x squared plus 1. It is natural log of x, 1/2 times natural log of x squared plus 1 plus c. And that's my final answer. Let's do another that's similar. So here we have integration of x times the square root of x squared minus 16 integrated with respect to x. So x times root x squared minus 16 integrated with respect to x. Let's go ahead and use substitution to integrate this problem. So in this case, obviously the square root is the outside function. You could also thought of that as being raised to the 1/2 power. We'll actually do that exchange in a second. But the inside function has to be the function underneath the square root symbol. So the x squared minus 16 is going to be the inside function. Like I've said before, the more and more you do of these, the more natural some of these steps are going to be. The more natural it's going to be able to, the easier it's going to be to determine what your u is. So derivative with respect to x is once again equal to just 2x. And once again, I'll say du is equal to 2x dx, and then I'll divide both sides by 2. So I'm going to say 1/2 du is equal to x times dx. Now I'm ready for my exchange. The x dx, take that x out there. The x dx, I'll pair that together. So I'll take this x out there. And when I do my substitution, I'm getting the square root of u times 1/2 du. Now I'm going to place the 1/2 up front. Actually, let me just write it there, down this way so we're not changing anything. So square root of u times 1/2 du. Now, in order to integrate this, I'm going to rewrite it. Let me say that's equal. So I'm going to rewrite this. I'm going to put the 1/2 up front, and then instead of u underneath the square root, I'm going to call that u to the 0.5 power, or the 1/2 power. I'll use 0.5 just because it's easier to write. It looks a little bit nicer when I type it out. As always, doing the antiderivative, we're going to add 1 to that exponent. So u to the 1.5 power. When I take 1/2 and I divide that by 1.5, that's like multiplying the 2 times a 1.5 in the denominator. We get a 3. So 1/2 divided by 1.5 is 3. And so there you go. That's my antiderivative written with variable u. I want my antiderivative to be written with variable x. So that is 1/3 times x squared minus 16 raised to the 1.5 power, or you could have also called that the 3/2 power. And then we add on our plus c. So that is the antiderivative of this function here, the x times x square root of x squared minus 16. So that's the antiderivative that I was looking for. The antiderivative of this original function, or an antiderivative, some would say. Hopefully that makes sense. Now, not every case of substitution will always be a polynomial raised to a power. That's a common case, but we also could end up with something like this. Let's use substitution to integrate this. We want to integrate e to the 4x squared plus 5 and then times x with respect to x. In this case, we have e to an ugly power. And whenever we have e to an ugly power, well, not whenever, but a lot of times when we have e to an ugly power, we want that power to be our u. In this case, if 4x squared plus 5 is my u, then the derivative of u with respect to x is just 8x. And so I can do a differential exchange of du is equal to 8x times dx. Or since I don't see a coefficient of 8, I think I'll divide by 8 on both sides, and I'll do the differential exchange of 1/8 du is equal to x times dx. So now I'm ready to integrate here. The first thing I do, since my differential exchange is x times dx, I put the x next to the dx. And now I'm ready for substitution. Now here we have e to the 4x squared plus 5. 4x squared plus 5 is my u. So that's e to the u. X dx is 1/8 du. 1/8 du. Oh, I'm just going to pull that 1/8 out front, and I'll place it as the coefficient of e to the u instead of putting it in between the e to the u and du. This is an easy integration to do. It's one of our basic rules. Anytime we integrate e to my variable with respect to that variable, I just get back e to the u. So I just get back 1/8 e to the u plus c, because that is the antiderivative of 1/8 e to the u du, or 1/8 e to the u with respect to u. I do my back substitution. Remember, u was 4x plus 5, 4x squared plus 5, excuse me. So I get 1/8 times e to the power 4x squared plus 5, and then all plus c. So that is the antiderivative that I was looking for, or an antiderivative, the class of antiderivatives that I was looking for. That is what I get when I integrate this function. Again, when we had e to a weird power, we let u be that weird power. Let's do this next example. If you want to try this on your own, go ahead and push pause on the video and try it on your own. Otherwise, I will just keep going and doing it. So again, we have e to a weird power times some polynomial. So we're going to make that weird power. I shouldn't say weird power. It's not that weird. We're just going to make that exponent BRU. Hopefully, then at the end, I'll just be integrating e to the u times something. So if I let that be my u, then the derivative with respect to x is 2x plus 1. So my differential exchange is going to be that I can replace a 2x plus 1 times dx with a du. In this situation, I would probably do the factoring instead of a division, just because the 2x plus 1, I don't really want to divide and cancel out. So what I'm going to do is I'm going to take this integration and rewrite it. I'm going to factor out 2 from that lead polynomial, and then I'm going to take that lead polynomial and kind of put it in the back and place it next to the dx, just for my own visual sake. Some people do this in their heads. I can do this in my head, but when I'm writing out in the notes, I like to write out as many steps as it takes. And I'd rather be overly descriptive in my notes than less descriptive in my notes. So here we go. We have 2e to that power. That power was u, so I get 2e to the u. 2x plus 1 dx gets replaced with just a du. So just like the last example, I'm integrating a constant times e to the u. Anytime you integrate e to the u, you get back e to the u, of course, plus c. So I integrate 2e to the u, and I get 2e to the u plus c. Again, my original integration started with variable x, so I'll write my final answer with respect to variable x as well. So e to the u was e to the x squared plus x. So my final answer is 2 times e to the power x squared plus x, and then plus c. So that would be my final answer after doing the substitution process to find the integral. Now, again, notice that in this case, I chose to factor that coefficient. In the previous case, I did a division by 8 instead of factoring, but you'll get the same answer either way. Some people like to do division, sometimes people like to do factoring, and they're all one way or all the other. I tend to just do what looks easiest. Like if there's an easy factoring, then I use the factoring. If there's not, then I'll just use the division. So I kind of just pick based on the problem what I think is going to be easiest. Whether we do factoring up front and pairing with the dx, or whether I do a dx and then divide. All right, so let's take a look at the next example. The next example is using substitution to integrate secant 6x times tangent 6x with respect to x. So in this case, you'll see that there's actually 6x's inside of two different pieces. So we're going to let u be equal to 6x because it's a function that is inside kind of two different other functions. So here we go. Here we go. We let u be equal to the 6x because that's inside a couple of different functions. And the derivative of u with respect to x is simply going to be the number 6. So my differential exchange is that du is going to be equal to 6 times dx. I don't have a 6 out as the coefficient of anything, so I think I'm going to just divide and say 1/6 du is equal to dx. So that'll be my differential exchange. 1/6 du is equal to dx. So I take now I'm ready to integrate. So I do all of that in prep work of my integration. And now we're ready to integrate. So 6x is going to get replaced with a u. This 6x will also get replaced with a u. So we have two 6x's that we're replacing with a u. And the dx gets replaced with a 1/6 times du. I'll take the 1/6 out front and write it in front of the secant and tangent. Now, this is a nice thing to integrate because the antiderivative of secant times tangent of the same variable is just secant of that variable. So we get 1/6 times secant of the variable u when we integrate, and then we always have to tack on our plus c at the end. So again, the derivative of secant is secant times tangent. So the antiderivative of secant times tangent is secant. So that's our answer with respect to variable u. Our answer with respect to variable x, well, since u is equal to 6x, it's just secant of 6x So we end up with a final answer of 1/6 times the secant of 6x plus c. Notice that here we're saying the antiderivative of secant tangent, if it's not just the variable by itself, if it's not just x, what we do is we basically get secant of our argument, and then we divided that coefficient by 6. The original coefficient of 1 here by 6. So we got 1/6 secant of 6x plus c as the final answer. Let's do another trig function integration using substitution. Let's do an integration of sine of ax, where a is just any number, any real number in there. If you want to try it on your own, push pause and try it. Otherwise, I will do it in just a moment. So since a is a real number, we just let u be equal to the inside function, that's ax, and then the derivative of u with respect to x is simply the real number a. So my differential exchange, du is equal to a times dx, or if we divide, which is what I'm going to do, 1 over a times the differential du is equal to the differential dx. So that's what we get. And now we can start with our substitution. So in order to do this integration, I say, well, this integration is the same as the integration of sine of u. U is equal to ax, remember? U is equal to ax. Dx becomes 1 over a times du. I'm going to write this as du over there and then 1 over a in front. Integrating with respect to u, the antiderivative of sine is going to be negative cosine. So we're going to get negative 1 over a. That's just that 1 over a is a constant. So we're going to get negative 1 over a times cosine of u plus c. Well, u, remember, was just ax. So we end up with getting negative 1 over a times the cosine of ax plus c. And that would be our final answer there. Now, once you see that what's happening here is on our basic integration, if we have something like ax, if we have a linear piece inside of our argument, then the antiderivative looks like essentially the same thing, but we have to divide by an extra a in front. So we can guess what would happen if we took the antiderivative of cosine of ax. I don't have to do all of the work. I'm just going to say, well, the antiderivative of cosine is sine, so we're going to get sine of ax. But since we have an ax in there, we divide by a out front as well. So that's what's going to happen with cosine. We did this already with sine of ax, negative 1 over a cosine of ax. We actually did this previously with secants and secant times tangent. If you replace all the 6's by just the letter a, you'd get a general rule for the integration there. And so once you've seen this a few times, you don't always have to write the entirety of every step. You can just say, oh yeah, here we're dealing with ax, so we're just dividing by a. And in the same vein, that's how we get the formula for how we integrate e to the power ax. If you do the exact same process of substitution, you get 1 over a e to the ax plus c. So you do that exact same substitution process and you'd get this. And so once you've seen this pattern a few times, You don't have to go back and do a whole substitution on every single one. For other problems, you probably do want to go back and do the substitution process. So let's do another example. Let's look at example 10 here. We're going to integrate 10x times sine of x squared plus 15 with respect to x. So we're going to integrate this one with respect to x. And in this one, you probably do want to do a substitution process just so you keep everything straight. On some of the more simpler ones, like this or like this, you might be able to jump to the final step once you've seen how it goes. But on this one, I think I'll do the entire process. So if you want to try this on your own, go ahead and push pause. Otherwise, I'm going to do it now. So our inside function is x squared plus 15. The derivative of u with respect to x is going to be equal to 2x. So my differential exchange is going to be du is equal to 2x times dx. Now, in a previous problem, I divided that coefficient of 2. I ended up with almost the exact same thing. I could divide right now if I'd like, or I could notice that this coefficient of 10 is just as I can factor that. So whichever way you want to do this, I think I'm going to factor that coefficient of 10. So I'm going to leave it as is. So I want to find this integral. And I'm going to pair the 2x with the dx. So 10x is going to be factored into 5 times 2x. And I'll put the 2x in the back. So when I substitute, I'm going to get 5 times the sine of u times du. 5 sine u du. And I want to integrate that. Once I integrate that, the antiderivative of sine is negative cosine. So negative 5 times the cosine of u plus c is the antiderivative or the class of antiderivatives. Now I'm going to do an unpacking. I say unpack because I kind of think of this as packing this and packaging this into a nicer form to integrate, then integrating, and then now I'm going to unpack back into the variable x form. So that's going to be negative 5 times cosine of x squared plus 15 plus c. That's one of the analogies that I use on this substitution. I want to start with something in x, package it in a form that's easy to integrate, then integrate in the easier to ship form, and then do that. It's kind of like getting an IKEA package in the mail. You know what it's going to look like, but they package it into very efficient shipping containers, but then you have to reassemble it yourself. But it's a lot easier to ship this way in the nice package form. Hopefully that's not too obscure. But so this is the antiderivative or the class of antiderivatives that I was looking for. This is how we integrate 10x sine of x squared plus 15 with respect to x. Let's do a couple more that show some different techniques. So here's another example where we can use substitution. We're going to integrate natural log of x divided by x with respect to x. So with this one, it might be a little bit difficult to see, but if you think about this, this is the integration of natural log of x multiplied times 1 over x when I break it down. So natural log has a derivative that is 1 over x. So in this case, it'll work out really nicely if I let u be equal to the natural log of x. Again, I'm using parentheses there. That is because when I take the derivative with respect to x, I'm going to get 1 over x. And so I can do a nice differential exchange where I let 1 over x times dx exchange for my du. And if I let that happen, then this integration becomes u times du. That's a very, very nice integration. That's something that I can find the antiderivative of with using basic rules. So I'm going to get 1/2 times u squared plus c. Now remember, u is the natural log, so 1/2, oops, excuse me, is going to be times natural log of x quantity squared. Now again, that's not the same thing as natural log of x squared. That's the natural log, the entire natural log being squared, not just not the argument squared, but the entire natural log squared. So that would be my final answer. 1/2 times the natural log of x squared plus c. Again, the natural log is inside the parentheses, and inside that parentheses, everything's being squared. Hopefully that makes sense. Again, natural log only can work when you plug in positive values, so some people would write absolute values around the x. I typically do not do that. So in this case, natural log, setting that to be my u, worked out nicely. Let's take a look at this rational function. Now, this is an interesting use case scenario of substitution because we're going to use another property of this substitution to deal with this integration. So here we go. We have a rational expression, and basically the idea here with substitution is that I can use the denominator in this instance. If I use the denominator of x minus 8 as my u, then I can do some nice algebraic techniques. I'll show you this in just a second. Now, before I move on, we're also going to need, before I move on, we're also going to need something else. Because when I take the derivative with respect to x, I'm just going to get 1. Derivative of x minus 8 with respect to x is 1. So my differential exchange is du is equal to dx. That's the easiest differential exchange there is. Just replace the dx with the du. Now, that allows me to replace the denominator and to do the dx, but now I have this numerator of x plus 2. So what I'm going to do is I'm going to go back up and realize that if u is equal to x minus 8, then I can actually replace any x I see with a u plus 8. So I could have thought of replacing the u, or replacing the x minus 8 with a u, or I can also replace any x I see with a u plus 8. Think about what that does to my integration. When I start to substitute, let's go ahead. Now I'm ready to integrate. So now I'm ready to integrate. When I start to substitute, x minus 8 gets replaced with a u. So this x minus 8 gets replaced with a u. The dx gets replaced with a du. And now I have this weird numerator to replace. But since x is equal to u plus 8, if I want to write that numerator with respect to u, I can say it's going to be u plus 8 plus an additional 2. Now, this might not look nicer, or at least this might not look a whole lot nicer than my original integration, but it turns out it is, because we get u plus 10 on the numerator. The denominator is just u. And that's a fraction I can easily divide. So when I divide that fraction, u divided by u is just 1. And then 10 over u, while that doesn't divide nicely, I do know an antiderivative of 10 over u. Now I'm ready to take the antiderivative of 1, which is just 1u. Again, we're doing this with respect to u. So when I take an antiderivative of a constant, I get u because that's the variable. And then the antiderivative of 10 over u is 10 times the natural log of u. So being able to have a single variable in the denominator was really nice because that allowed me to do division and then end up with pieces, specifically 2 pieces. Let me rewrite this. 2 pieces that I could integrate. I can integrate the constant of 1. I can integrate the constant of 10 over u, both very easily. And now I'm ready to back substitute. Remember, my u was x minus 8. So I replace the u out front with an x minus 8. And then I go 10 times the natural log of x minus 8 plus c. Once again, like I always say, I'm writing parentheses around this, but a lot of people would write absolute values around the argument inside the natural log because natural log can only take positive arguments. But that's that. If you want to drop these parentheses out front, you can. They're not doing a whole lot. But letting u be equal to the denominator in this rational function was the trick. U is the denominator. That allowed me to divide easily once I got to this stage. But that means I have to mess around with the numerator too. Replace the x with u plus 8 as long as u is equal to x minus 8. So that's, again, another tool in our substitution toolkit that we can use. Now, here's another example where we can utilize a similar technique to example 12, to that rational function technique. So we have the integration of x times the square root of x minus 4. Trying to do this with basic methods would be very tough. But this is doable with substitution plus a little algebraic manipulation. So if I just set u is equal to x minus 4, then when I do the derivative of u with respect to x, I get 1. So once again, my differential exchange is that du is equal to dx. Now you could also have coefficients up here. I chose to do fairly straightforward problems. And that takes care nicely of the square root. It also takes care of the dx, but I also end up with this sort of rogue x out front. So how do I take care of that rogue x out front? Well, I just noticed that if u is equal to x minus 4, then u plus 4 can replace any x I see. So now I'm ready to substitute. The x minus 4 underneath the square root is going to become a u. The dx turns into a du, and the x turns into a u plus 4. Now be careful when you do that. That u plus 4, quantity u plus 4 has to multiply times the square root of u. So when I do my substitution with algebra, I get that. Now the square root of u is also known as u to the 1/2 power. So again, I'm going to rewrite this. I'm going to get u plus 4 quantity times u to the 0.5 power, or the 1/2 power, du. And then I'm going to distribute that u to the 0.5 in. U times u to the 0.5 is going to be u to the 1.5 power. Four times u to the 0.5 is just 4 times u to the 0.5. So I get that integration, which, again, so this is my algebraic manipulation, is I just distribute the square root of u, and I multiply that times u. That gives me u to the 1.5. 4 times square root of u gives me that. And now I'm ready to integrate, because each of these two terms individually is pretty easy to integrate. I go u to the 2.5 power times coefficient of 1 over 2.5 plus u to the 1.5 power times coefficient of 4 divided by 1.5, and then plus c. So again, remember u here is x minus 4. So when I rewrite this in terms of x, 1 divided by 2.5 is actually 0.4. So I'm going to write that. I'm going to write 0.4 times x minus 4 raised to the 2.5 power, plus, if I do 4 divided by 1.5, that's 2 2/3, or 8/3. It doesn't matter how you write that. I'll write it as 8/3, I guess. And since I'm writing things as fractions, maybe 0.4 should be written as a fraction too. It doesn't really matter, but I'll keep it as 0.4 for right now. But substituting u, replace that with x minus 4, gives me this. I know I have all kinds of different, I have a lot of decimals, and then I have this fraction, but hopefully that all makes sense. So this is another time where when my du dx exchange, my differential exchange, and my straightforward u exchange leave me with some extra x's around, I can just replace those extra x's with, in some cases, I can replace those extra x's with like a u plus 4, like I did here. Okay, so I can't always do that, but when I have u is equal to a linear function in x, I can always do that. So I can always do it in the linear exchange cases. In the quadratic or higher cases, I can't do that. So that's a lot of different substitution techniques. And in all of the examples, all 13 examples that I just gave you, substitution always worked as long as we combined it maybe with some algebraic manipulation. Well, we can use substitution to evaluate definite integrals as well. Now, when we do substitution and use definite integrals, we have to be careful that the bounds are going to be with respect to x, or whether the bounds are going to be respect to u. So I do have to worry about like what the bounds are, but other than that, it's a pretty straightforward process. We find an antiderivative, we plug in the bounds. If we're plugging into x, I need to make sure that those are x bounds. If we're plugging in for u, I need to make sure that those are u bounds. So I'll do an example pretty quickly. Let's evaluate the definite integral from 0 to 2, x times 3x squared plus 5 squared. So the quantity 3x squared plus 5 is being squared and then multiplied times x. Now I'm going to go through this fairly quickly. We've done a lot of substitution examples. So inside function here is 3x squared plus 5. The derivative of u with respect to x is equal to 6x. So 1/6 du is equal to x times dx. If all of this looks familiar to you, it should, because this was example 3. So if you, without the bounds, this was the indefinite integral with example 3. So basically, I'm just going to go through all the steps. When we integrate, and I do my substitution, if I substitute in u, we'll get u squared. X dx gives me 1/6 du. So I'm going to go 1/6 du. However, this substitution, this substitution is not right with the bounds that I have. Notice that these bounds are with respect to x. So that means x goes from 0 to 2. What would u go to? U, when I plug in x of 0, is 5. And when I plug in x of 2, I get 3 times 2 squared plus 5, which is 17. So technically, my bounds should go from 5 to 17 on the u. Now, normally I just leave those off. I don't even worry about those because when we find our antiderivative, most of the time we unpack into the x values. And so that's what I would have probably done. I would have found the antiderivative, and then I would have unpacked into the x values. What I mean by that is go 3x squared plus 5 to the third, and then used the x value bounds. So plugged in the x value of 2 and then plugged in the x value of 0. When I plug in the x value of 2, I get 1 over 18 times 3 times 2 squared, that's 12, plus 5, that's 17, to the third. So 1 over 18 times 17 raised to the third power. That gives me 272.9444, which is 17 over 18. So I get 272 and 17/18 as the number when I plug in 2. Now when I plug in 0, I get 1 over 18. This is going to turn into 0 plus 5 to the third. So basically 1/18 times 5 to the third, which is 6 and 17 over 18. So what I get is 266 as my definite integral. And again, you just have to be careful that you use the bounds for x's when you're doing that, or if you were to plug in for u, you could have actually plugged in these bounds. You could have plugged in 17 in for u and then 5 in for u. Let me write that down here. The plus c won't matter. I could have done that. And either way, if I plug in 17, I get this. Plug in 5, I get this. Subtract them, you get 266. Now, for the most part, so I can do that using substitution techniques perfectly fine. But to be honest, most of the time when I have a definite integral like this, I just use my calculator and use the TID4's math integration function if I have a definite integral. So I would integrate from 0 to 2, I'd plug in x, and then I would plug in 3x squared plus 5 in parentheses raised to the second power, and then integrated that with respect to x. And I could have skipped all of the substitution stuff and just plugged in this into my calculator and came up with a 266. So for the most part, the questions that you'll see from me in my class in this section will be not the definite integrals, but rather the indefinite integrals. Because with the definite integrals, we can just use technology for those. And that's what I often do. I often simply just use technology and let my calculator find me the number that I get for this without going through the whole process of substitution. Now I want to just put it into the future that substitution is just one technique amongst many. It's a very nice technique and it works on a lot of integrals, but it does not work on every integral. If I tried to use direct substitution, like the U substitution technique that I'm using in this section, on this integration of x times e to the x, it wouldn't get me very far because this exponent is already nice and this is already nice. So if I let x be equal to u, I get the exact same integration as I did before. So we'd have to use a different technique there. And if I try to use u equals x squared minus 9, it'd turn out I'd get 1 over the square root of u, but then I'd have to do a differential exchange, and I need another x to do a differential exchange. So the x's wouldn't work out in that one. So the substitution technique is a very good technique and one of my favorite techniques, but it's not going to be very useful on every single integration that we encounter, every single integral that we encounter. So that's why we need some other techniques beyond this. And we'll look at some other techniques beyond just substitution in the next few videos.